last section of the chapter, 8-9, remembering properties of powers and roots. This is more of a little bit of review for yourself, but it's also a way to test special cases in following patterns and knowing alternative ways of rewriting the same expression. So that's what we're going to be talking about today. The properties of powers here, little memory here. Same base, you're multiplying. Exponents, you add them together. Power of a power property. One base, two exponents, you multiply your exponents. A power of a product property means you put the N on the A on the B. So no matter how many things there are there, that exponent has to go on every single term. Negative exponent property. If you have a negative exponent, to make it positive, you move it to the bottom. If you have a negative exponent in the bottom, people, you have to remember, then you move that to the top. Okay? Quotient of powers property. Same base. We're dividing here. You subtract the exponents. Power of a quotient property. Okay? The N goes on the numerator and it goes on the denominator. No matter how many things are on there, that N goes on all of it. Our properties of square roots. Your square root property, the square root of A times the square root of B is equal to the square root of AB. Okay, you can multiply those two things together as long as they have the same index. Same thing here with quotient of square roots. As long as they have the same index, you can take the square root and divide them. Okay? Testing a special case. Because of calculators, a strategy called testing a special case is often possible. You can use this strategy to verify your reasoning. So let's look at example 1. Emily was not sure how to simplify x to the 5th times x to the 6th. She felt the answer could be x to the 30th, 2x to the 11th, or it could be x to the 11th. Which is correct? Go to your calculator. And if you watch here, I hit my y equals. I'm going to let y1 be x to the 5th times x to the 6th. Oops. Go back here and delete that. I'm just going to clear it all out. X to the 5th times x to the 6th. Okay. Now, what she thought it could be is x to the 30th. So I'm going to put x to the 30th in for my y2. For my y3, she also thought it could be 2x to the 11th power. And for my y4, she also thought it could be x to the 11th. So we're going to see which one it works for. So I'm just going to go to my table, and what I'm going to look for is, I'm looking for which ones equal each other. Okay? Which ones equal each other? So I'm going to change my table setup to go from 1 and go up by 1s because I don't need decimal points. Okay? But if you look for 1, it looks like y3 is going to be out because for y1, okay, it's the same. It's the same for y2. Sorry, y2 is the same. y3 is not the same. So 2x to the 11th is not working. Okay? So it's in between y sub 2 and y sub 4 because they're both the same. If you come back here, if you look at 2, This one's 2048. Is this one 2048? No. Which one's 2048? Well, which one's 2048 is y sub 4. So x to the 5th times x to the 6th is equal to x to 11th. And we check that by looking at our calculator. Okay? Showing that a pattern is not always true. If you remember, a counterexample is proving that something is false. So if it asks for a counterexample, you're basically saying, hey, I just proved you're wrong. So in example 2, it says Sir Lancelot's assistant, Squire Root, notice that 2 to the 3rd power plus 2 to the 3rd power is equal to 2 to the 4th power. Since 8 plus 8 equals 16, 2 to the 3rd is 8 plus 2 to the 3rd is 8, 2 to the 4th power is 16. He guessed that in general there is a property x cubed plus x cubed has to equal x to the 4th. He tested a second case by letting x equal 0. So he put 0 in for x. 0 squared, or 0 cubed plus 0 cubed, 0 plus 0 equals 0 to the 4th, which is also 0. So he concluded that the property is always true. Is he correct? Well, here's my counterexample. I'm going to let x equal 1. So if I let x equal 1, that means 1 cubed plus 1 cubed equals 1 to the 4th power. Well, 1 cubed is 1, plus 1 cubed is 1, and 1 to the 4th is 1. Well, what's 1 plus 1? 2. Does 2 equal 1? No. So when x equals 1 is my counterexample to prove Sir Lancelot wrong. Let's look at example 4. If the quantity 9q to the negative 5th divided by 6q to the negative 3rd all to the negative 7th power equals aq to the n, what are the values of a and n? Well, I'm just going to go ahead and do the whole problem, and then we'll figure out what a and n is. So I'm going to break this down. I have a negative 7 power, so to make that a positive 7, the numerator and the denominator has to flip-flop. So it's 6q to the negative 3rd divided by 9q to the negative 5th, all to the 7th power. Just by flipping them, made this positive. Okay? Now, I'm going to do the stuff inside here. Because I know I can reduce 6 over 9. 3 will go into both of them. 3 goes into 6 twice. 3 goes into 9 3 times. Okay? Q to the negative 3rd divided by q to the negative 5th, we subtract our exponents. So I have to subtract a negative 5. Well, minus a minus becomes a plus. So q to the negative 3 plus 5 is q to the 2nd. So q to the 2nd stays on top. This is still all to the 7th power. Now, what I need you to remember is this 7th power goes on everything in here. So it becomes 2 to the 7th, q to the 2nd times 7. What's 2 times 7? 14, divided by 3 to the 7th. Equals. Well, what is 2 to the 7th? 2 to the 7th in this case is 128. And 3 to the 7th is 2,187. So, we're all done. The question is, what are the values of A and N? Well, A is my fraction. A equals 128 over 2,187. N is my exponent, and my exponent in this case is 14. Okay? This is how your work should look. We're not able to do problems anymore in just one step or doing these things in our heads. We're going to have to take our time and methodically go through it and make sure we remember each of our properties to get our answers. That's all I have for you today. We'll see you tomorrow. Thank you.